Hi, in this video, we introduce MD-Tree, a new model diagnostic method that uses loss landscape metrics without requiring access to model configurations or retraining. Consider a real-world scenario of model development, given two trained models, Model A and Model B. If we use traditional diagnostic techniques, such as validation-based metrics, we can only determine that both models are underfitting based on their training and validation errors. However, these metrics don't provide actionable insights about how to take next step. Should we take the same operation, like increasing the model size, for both? The answer is no. By using the room for improvement metric defined in our study, we see that the failure sources leading to underperformance are different for these two models. Model A has an insufficient model size issue, while Model B has an optimizer issue. Thus, the most effective operations are different. Room for improvement quantifies the impact of failure sources on model performance, which can be attributed to three key hyperparameters in the radar plot. The details of definition will be provided later. Similarly, in another pair of cases, the failure sources that lead to two overfitting models are also different. This case study motivates our model diagnosis framework, which aims to identify the most significant sources of failure causing a trained model's underperformance. Our study focuses on a simplified configuration, considering three key hyperparameters: the number of model parameters, the amount of data, and the optimizer hyperparameter, such as batch size. We identify failure sources as suboptimal choices in these basic configuration parameters. Specifically, we examine four potential sources: small and large optimizer hyperparameters, small model size, and insufficient data. Our diagnostic objective is to determine which failure source most significantly impacts performance when multiple issues are present. This understanding is crucial for model development, helping developers allocate budgets between operations such as getting more data, increasing model size, or refining hyperparameter tuning. The conventional way of diagnosis involves retraining with different configurations, such as hyperparameter searches guided by the validation metrics. However, this method becomes impractical with pre-trained models, as accessing the original datasets and configurations is often challenging. In this work, we introduce a new framework that predicts diagnostic answers directly as a classification problem, without needing the original configuration or retraining. Here, we define the diagnostic questions. As mentioned earlier, these questions compare the significance of four potential failure sources. To quantify the impact of these failure sources, we introduce the metric room for improvement. It measures the potential performance gain if a specific failure source is addressed. For example, this is definition of room for improvement for small model size. The calligraphic E represents validation error, calligraphic A represents the model training process. The configuration to be diagnosed is F0 and can be visualized as a point in the 3D hyperparameter space, where the axes represent the three basic hyperparameters. By increasing the model size within an allowable range from P to P max and fixing other two axes, we identify an optimal configuration F star. The room for improvement is then calculated as the performance difference between F0 and F star. The room for improvement of other failure sources are similarly calculated by optimizing their respective hyperparameters. The diagnostic objective is formulated as binary classification labels using room for improvement. In the first question, capital G represents the difference in the room for improvement between two failure sources, large and small optimizer hyperparameters, denoted as MT upper arrow and MT lower arrow. If G is greater than 0, it indicates that the large optimizer hyperparameter has a higher room for improvement and is the more severe failure source. Conversely, if G is less than 0, the small hyperparameter is the more severe. In the second question, capital G represents the difference in the room for improvement between two sources, small model size MP and optimizer hyperparameters MT includes both large and small cases, MT upper arrow and MT lower arrow. If capital G is greater than 0, it indicates that the small model size is the more severe failure source, otherwise another source is more severe. Our approach consists of two steps. First, we extract features from trained models that are associated with failure sources. We employ loss landscape metrics, demonstrating that these metrics outperform traditional validation-based metrics for diagnosis. This advantage is illustrated through the case studies introduced earlier. Loss landscape metrics captured the distinction between the two underfitting models. Model A, with poor connectivity, is affected by model size issues, while Model B, with good connectivity, suffers from suboptimal optimizer settings rather than model size. This can be further shown with another pair of examples, showing how loss landscape metrics, such as sharpness, can distinguish different failure sources among two overfitting models. The second step is to classify the diagnosis results based on the extracted features. We use a decision tree-based method, which partitions the hyperparameter space into multiple regimes where models within one regime share similar failure sources. This approach is inspired by the studies on statistical physics viewpoint of learning and its connection to model diagnosis. Recent work in this line of study used loss landscape metrics to identify regimes within a 2D hyperparameter space, predicting test accuracy. Our approach borrows the regime partition and adapts it to predict failure sources. Our tree has fixed structure and is constructed hierarchically, prioritizing metrics that cause sharp transitions in hyperparameter space, such as training error and mode connectivity, that documented in prior work. The visualization here shows the construction of an MD tree. The red and blue values indicate the binary labels for the first diagnostic question. The tree structure is fixed, and only the threshold values of each node are learned from a training set. On the left, the learned tree branch shows that models with a training error less than or equal to a certain value are assigned to regime 4. This regime is predicted to have a failure source related to a large batch size. On the right, we see how models allocated into regime 4 are distributed. The X and Y axes represent loss landscape metrics, and the colors indicate the ground truth labels. The tree further partitions regime 3, classifying some models with the blue label. Now the tree construction is completed. The first key finding is that the MD tree's predictions are interpretable. For example, models in regime 2 are diagnosed with a large batch size failure. This regime are identified with poor connectivity and sharpness. This is indeed an issue well documented in large batch training studies. The second finding is that the decision boundaries of MD tree are linearly separable and can generalize well to the test set. In contrast, using validation metrics results in a more complicated and less transferable decision boundary. We compared the diagnostic accuracy of the MD tree with two baseline methods that use validation-based metrics or hyperparameters as features in a standard decision tree. Our results demonstrate that the MD tree consistently outperforms these baselines across 2 diagnostic tasks and 5 transfer scenarios. Here are evaluation results for the first task and scenarios of dataset transfer and scale transfer. We apply diagnosis methods to a one-step hyperparameter change, which executes the suggestions to address the failure source predicted by the diagnosis method. We find that more accurate diagnosis like MD tree can lead to higher performance improvement. Thank you for listening. We will publish the model diagnostic datasets with metrics for future research. Please check our paper and code for more details.